We are back, and we're starting chapter 14, acids and bases, and we're going to be discussing both acids and bases and equilibrium conditions for acids and bases. So we're continuing on. Chapter 13 was equilibrium. We're still doing equilibrium. We're just doing some more types of equilibrium. So first we need to go over some definitions of acids. We have an Arrhenius definitions. Acids produce H plus in solution. Bases produce OH minus. There's another definition, the Bronsted-Lowry. Notice if you produce an H plus is just a proton. So acids are proton or H plus donors. They give away H pluses. Bases are proton acceptors. They accept H pluses. Here's an example. We have HCl and H2O. So the acid, notice the HCl gave away this H plus to the water. So the HCl is going to produce H plus. That's the Arrhenius definition. By the way, H3O plus, called hydronium ion. It's the same as H plus. H pluses don't exist by themselves. They always attach onto a water. So this HCl is producing H plus. It's an acid. Or we could see HCl is donating its H to the water to become H3O plus. And H2O is accepting the H plus. So it's a base because bases accept protons. Here we go, acid and base. Note that H3O plus is just hydronium. Okay, there's also something called a conjugate acid-base pair, and we could look at this right here and figure out what the pairs are. Oops. Oh, let's do this on this top part. So we want to look at who's the acid in this pair and who's the base in the pair. So the pairs differ only by one proton. So these two would be a pair. These two would be a pair. They differ only by one H plus. And the acid is the one who's going to donate the proton, or it always has an extra proton. So here's my acid. Here's my base. The base is going to accept the proton. The Cl minus is the conjugate. The conjugate what? Base or acid? Well, we started with an acid, and the acid becomes the conjugate base. That's the Cl minus, and the H3O plus would be our conjugate. Let's see, we started with a base, so this would be the conjugate acid. So let's look at this next one. Let's find our pairs. What looks like the other one, the HA looks like the A minus, and the H2O looks like the H3O plus. They're just different by one H plus. And the acid has an extra H plus, so here's my acid. Here's my conjugate base. And between the water and hydronium, here's my acid. Here's my base. The acid has an extra H plus compared to the base in a conjugate pair. Okay. Let's see what else we're going to learn today. Oh, here's just a pictorial of that reaction. So let me erase all this so you can see that better. Okay. So right here is my acid, and my acid is going to lose its H plus. This little white ball is an H plus. So we have the purple by itself with a negative charge. And then our water is going to take this little white ball, which is an H plus, and attach it onto the actual molecule. Okay. Ka's. This little A down here stands for acid. It's the same K that we've been talking about all along. It's just an equilibrium constant. But now it's for an acid equilibrium, and we call this acid dissociation constant. Equilibrium constant for an acid reaction. And a Ka will always be equal to products, H3O plus times A minus, see that, products, over reactants, just we haven't changed anything around, and the reactant is HA. Why am I not including the water? Why isn't water in the Ka expression? Because it's a liquid and we don't include liquids. Okay, just a note here, when you see this word dissociate or ionize, we're talking about breaking apart or to cause ions to be created. So we will talk about the dissociation constant. Later we will talk about percent dissociation, and you need to know what that means. All right, section 14.2. We're moving quickly. Oh dear. Okay, acid strength. There's some information you need to know. As Ka increases, the acid strength increases. So if we're comparing two different acids, the one with the larger Ka is a stronger acid. All right, what else do we have? Ooh, another important thing. If an acid strength increases, the conjugate base strength decreases. So the stronger the acid is, the weaker the conjugate base is. So for very strong acids, the conjugate bases are extremely weak. Oh, there we go. That's what I just said. This second bullet right here implies the third bullet, that strong acids, Hibber-Hickel-High, Hono-Hickel-O, H2SO4, have extremely weak conjugate bases. In fact, the conjugate bases of those strong acids are weaker than water when water is acting as a base. Okay. So if we have a really strong acid, that means the equilibrium lies to the right. So the stronger the acid is, the farther to the right lies the equilibrium position for the acid reaction, and the weaker the conjugate base is. So as acid strength gets stronger, conjugate base strength gets weaker. We said that already up here. We're just repeating it. It's a very important note. Make a little, highlight this about the conjugate base strength decreases as acid strength increases. Okay, we said if an acid is stronger than another acid, the equilibrium lies farther to the right. Well, if we have the opposite, if an acid is weaker than another acid, the equilibrium will lie farther to the left, and the conjugate base strength is stronger. So as acids get stronger, comparing different acids, the conjugates are weaker. As different acids, comparing them, the weaker the conjugate, the weaker the acid, the stronger the conjugate base. Okay, so you're going to fill this in now. So just think about this for a moment. I'm going to pause. I want you to think. You should be thinking about, is the Ka large, bigger than 1, smaller than 1, small? So if equilibrium lies to the right, you should just think about the K values in general. Are the Ks large or small, bigger than 1, smaller than 1? Okay, go ahead and pause. The answer is about to show up. Pause. Make sure you pause. Okay, and one more, fill in the blank. If equilibrium lies to the left, the value of Ka is, go ahead and pause. I'm going to fill this in. And there you have it. So if equilibrium position for a reaction is far to the left, we already know that that means the K is small and K is less than 1. All right, we're going to move on. All right, we have a problem now. We have a solution of sodium with an anion. A minus is just an anion. This A minus represents a generic anion. And the weak acid would be H with A, where A is the generic anion. So we have A minus plus water makes HA plus OH minus. I'm just showing you the base, the acid, the conjugate base, the conjugate acid. Which way will the equilibrium lie? So you have to think about who's stronger, who's weaker. So if we have an water versus HA, you want to think who's the stronger acid. And the stronger acid causes the reaction to go in the opposite direction from the stronger acid. Also, you could think of looking at the bases. We have A minus versus OH minus. If we have weak acids, their conjugates are weak bases. And think about OH minus. OH minus is a really strong, very strong base, sorry. A minus is a weak base. So who's going to take control? Let's look. These stronger acids and bases compared to these weaker acids and bases are going to take control, and their equilibrium will be pushed to the left side. If that didn't make sense, you might want to listen to that again. Okay, now think, if the reaction lies to the left, is Kb. Kb would be the equilibrium constant for this reaction, which is a base reaction, because we have a base reacting with water. So this would be for a base reaction. We're just asking, is the equilibrium expression for this reaction greater than or less than 1, given that the equilibrium position lies to the left? So figure that out. Go ahead and pause. Here we go. Since equilibrium lies to the left, Kb has to be less than 1, because that means the reactants are smaller than the products. Okay. Does this mean A minus is a strong or a weak base? Well, given the fact that we're lying to the left, this reaction doesn't get pushed to the right very much. Hopefully you figured out A minus is a weak base. The other thing to recognize is whenever you have a weak acid, its conjugate is always a weak base. So all acids, the conjugates of all weak acids are weak bases. Okay, here is just a table of some Ka values for different acids. So I've given you some Ka values, and you're going to arrange the following 4 compounds from weakest to strongest as bases. You're going to explain your answer. Notice these are Ka values over here, not Kb values. So we have the names of the acids right here, the formulas of the acids are over here, and the conjugate bases are right here. So we want strongest to weakest. Now, in order to do this problem, you need a hint. First, you need to look up the Ka values for HCN and CH3COOH, that's hydrogen cyanide and acetic acid. And then also we're going to have to look at the notes on the first page for section 14.2. We're going to think about Cl minus versus water, and we're going to look back at the other page. Okay, so here's page 14.2. The larger Ka, the stronger the acid, and the stronger the acid, the weaker the base. So we can compare Ka values of HCN and acetic acid. Whichever one has a higher Ka, its conjugate is a weaker base. Now, one other thing to notice is strong acids have extremely weak conjugate bases. The strong acids' conjugate bases are weaker than water as a base. Okay, well, that just answered one of our little questions over here. Here we go. You had your hint. Now, between Cl minus and H2O, Cl minus is the conjugate of HCl, so that means Cl minus is a weaker base than water. And by the way, the Ka for water, I gave that to you right here, 10 to the minus 14. So we can just compare all the Kas now. So HCN, Ka is 10 to the minus 10. That's a 10 there, on the order of 10 to the minus 10. Acetic acid, the Ka is on the order of 10 to the minus 5. So acetic acid is a stronger acid than hydrogen cyanide is, which means this is a stronger base than the Cn minus, because this is a weaker base than Cn minus, because the Ka for the acid is bigger than the Ka for the other acid, so this base is stronger than this base. Let's look at all of that information. Got it all summarized over here. Take a moment to read that. Okay, so here's the answer over here. So Cl minus is the weakest base because its conjugate is a strong acid. And next would come water. Next would come the acetate because of the Kas. And the last would be Cn minus. Pause if you need to go ahead and read through that. Next section, 14.3 and 14.4, the pH scale. Now, this is really a review. Here's some information. If you need to pause, read through that. You've got your 6 equations. And you use these 6 equations to calculate pH, pOH, et cetera, et cetera. Okay. I said this earlier. Note that H plus and H3O plus, hydronium is H3O plus, can be used interchangeably. And I said this earlier, and now it's written out. Hydrogen ions do not exist by themselves in water. They attach onto water molecules via this reaction, creating hydronium. Okay, so we're going to use those equations to solve these three problems. Now you're going to want to pause. I have all the answers up. I don't have these worked out. I'm expecting you know how to use these equations. I will go through number one with you real quick, how I got the answers. So to get pH, you do negative log of H+. HI is a strong acid, so that means the H+ concentration is 0.1 molar. So pH is just negative log of 0.1. Put that in your calculator, you get the answer 1. pH plus POH equals 14, so POH is 13. H+ is 10 to the negative pH, or it was given to us already. H+ right here is 0.10 molar. And OH minus, I could do 10 to the negative pH, or I could use this equation. Both give you the same answer. Okay, number two, hopefully straightforward. You just use those four equations. You're given pH. You can calculate POH from that. Use H+ is 10 to the negative pH. OH is 10 to the negative POH. The third one is a little bit tricky because you have to realize here's your OH minus. And so the OH minus will be 0.15 times 2, because you have 2 OH minus in this strong base. So the OH minus is 0.3 molar. You had to do that one first, actually. From that, we get the POH. Just we take the negative log of 0.3, which would give us 0.52. And then 0.52 subtracted from 14 gives us 13.5. It's okay. And then we do 10 to the negative pH to get H+. Gives you this number. Okay, we're getting to the end here. Calculating the pH of weak acid solutions. Here we need to use our handy-dandy ice boxes, and I'm going to work this out and talk through it. First, you need to figure out what your reaction is. We've got NaCN. Whoa! We've got NaCN, and I'm going to need to remind you of an equation we knew before, but we can't do that yet. So NaCN, I don't care about the Na+. I don't worry about that in my reaction. I just worry about the Cn-, which is a base. You had to recognize I've given you the Ka for an acid, so Cn- is a base. If we have a base reaction, you always add water to whatever reactant you're given, and then you look at this and you say, what am I going to make? Well, if this is a base, it's going to steal an H+ to become HCN. And what's left? It's stolen H+ from the water. All that's left is OH-. Okay, here's my reaction, and I'm going to do an ice box, ICE. Cn-, what was the concentration? Right here, 0.75 molar. I don't worry about the water. These were not given. Those start out as 0. I don't worry about them. Minus X, 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 0.75 minus X, X, X. So far, so good. Now, I gave you the Ka for HCN, and we had an equation last year that you're going to use now. Ka times Kb is equal to 10 to the minus 14. So that's how we calculate Kb's. This reaction here is not a Ka reaction because I have a base as a reactant. This is a Kb reaction. I need a base dissociation constant as opposed to an acid dissociation constant. So I calculate my Kb right here. Okay, so all I did was I divided this 10 to the minus 14 over the Ka given right here, so over 6.2 times 10 to the negative 10, and I got 1.6 times 10 to the negative 5. I hope that's correct. So now I have my equilibrium row, and I just do products over reactants. X squared over 0.75 minus X is equal to Kb, which is 1.6 times 10 to the negative 5. All right, now in solving for X, this is one of those assumptions moments. You could solve a quadratic, but that gets ugly and messy. So instead, I'm going to assume that 0.75 minus X is approximately equal to just 0.75. I'm assuming X is much smaller than 0.75. So I'm going to assume that this denominator is just 0.75, and I will solve for X, and I get Okay, I get x is 3.46 times 10 to the negative 3 when I solve that equation. And I note this up here. Note that is my OH minus concentration. And the question asked for, what did the question ask for? Find the pH. I got to be a little careful now. So I got to find the pH. I know that OH minus is 3.46 times 10 to the negative 3. So I can do the POH. POH is just negative log of OH minus. Okay. Plugging that in my calculator, I get pH is 2.46. pH is 14 minus 2.46, which is approximately 11.5. There we go. That's our answer to that problem. Last problem for the day. Okay, this is another kind of quirky one. You'll see why in a moment. We have an acid this time, which means we're going to have a Ka. We always add water to whatever the chemical is. And this is an acid now, so the acid's going to give its H+. Acids are proton donors. It's going to give its H+ to the base in the reaction, right there. And we make H3O+, and we're left with, oops, oh dear, hold on. C3H5O3 minus. Okay, and we're going to make our icebox, ICE. Now what if, I've actually given you percent, some information by telling you this percent. I gave you the initial concentration, 0, 0. Now, the change, if I tell you the percent dissociation, I've told you X. I've told you that 3.7%, which is 0.0037, 3.7% of 0.100 dissociated. That's how much dissociated. It's how much reacted. So that is just 0.00037. That is how much, 3.7% of this 0.1 dissociated. So the change minus X, XX, is equal to 0.00037. So this will be 0.1 minus 0.00037, and these will just be 0.00037, 0.00037, and that tells us Ka is just x squared over 0.1 minus x, oops, equals. Now I could make my assumption and just use 0.1 on the bottom here. I do have the value I need to subtract from there, but I'm going to see that 0.1 minus this whole number really is just 0.1. And I get 1.37 times 10 to the minus 8. And there you have it. Oh, I hope you could hear that all. I was not holding my microphone for a little bit, but hopefully you got it.